we also care about how quickly this approaches the exact kernel. And so we look at it as the variance of the kernel. We know the expectation is the true kernel, so the variance also we find that it goes down as you increase d. And also the variance of the RKS kernel is close to the variance of the fast food kernel. And finally, one key problem with fast food is that there's dependence between the rows of a block. So we don't have this independence Gaussian random matrix. You have a product of a bunch of matrices which introduces dependence between the rows. So we look at the covariance between the rows, and this is the plot of the covariance. So you see that, the diagonal is the variance of one row, but the covariances are actually fairly small. If you were to do this for RKS, you would basically get zeros on the off diagonals, or very, very close to zeros. And this is sort of one of the key insights that we're trying to leverage to prove better theoretical bounds on the fast food approximation.
Yeah, so when you use kernels for classifying, and what you're ultimately interested in is not how well you're approximating the kernel, is how well your classifier is doing. So you're looking at the risk. And so you want to be able to say, so again, k hat is a random approximation. So we want to know whether with high probability, if I'm drawing this matrix or these blocks of matrices, I'm going to approximate the kernel really well. So again, you could use concentration bounds, but because we still have some, although low, we still have some variance between the rows, and because these are Gaussian, if you had zero covariance, then they would be independent. You could use, Hepning's inequality or something straightforward, and actually that's what Random Kitchen 6 uses. They have a better bound on concentration, although both perform very similar. So let's suppose you have this bound, and what it's saying is, with high probability, when I compute my estimated kernel is not too far away from the true kernel, then it's straightforward if you look at the empirical risk and the functions that minimize those. So there's another key difference here is that the Hilbert space you're using for k hat is different. You're in two different Hilbert spaces, but still, you can still formalize and find the empirical minimizers in terms of the kernel matrix, or k hat, and the true one. And just look at the empirical risk and see how they compare. It's just straightforward from that probability. No, this is straightforward by itself, that these two risks, if the loss function is L Lipschitz, then they don't differ by this much. So if with high probability this soup up there is less than epsilon, then you can get this bound with probability of this 1 minus delta epsilon. Of course, what's delta epsilon, right? We would hope that the more rows you have in your matrix, the better it goes. So the more samples dependent samples in fast food you have, then it's going to actually decrease exponentially. So, and that's actually what it is in some sense. So if you have n blocks of fast food, then delta epsilon is going to decrease exponentially on n. The problem with n is that if you have a lot of, if d, the dimension of the vector is real big, then you might not have a lot of blocks. So you still want to make delta better. So what we just saw is the moral is that if you manage to get a better bound for this p, then you get automatically a better bound for the difference on the risks. And then we try a couple of things. So, so if you look again at W, the matrix that gives you, or the block, sorry, 30 seconds. Oh, the matrix that gives you the fast food, and they have two components, Hg and pi Hb. The first one is Gaussian. The second one can be seen like as a Markov process that is reversible. So you want to use something like Markov or Hepning's or something with the low variation of the rows to bound the first term, and then use Ledoux or some concentration for Markov process to bound the second one. We did try Ledoux, and the bound was trivial, so it didn't work very well. But it gives us an insight that we need to do something still with the variance. So that's what we are right now. And thanks for listening.
So one note that so Zoltán Szabó, he's a visitor from University College London.
Yeah, he gave
He's
yesterday.
here, right, and he has an X paper exactly on this.
He has a really good bond on RKH. Actually, using McDermott in this is the thing. Like in McDermott's case, when you have the random kitchen sinks, because the rows are independent, it works real well.
Yeah.
With fast food,
I
you
know.
have the high dependence on. You can get a bond that is not uniform, but if you want to bound the risk, you definitely want that.
So my point is, he's here today, so you
Yeah.
might want to talk to him.
Yeah.
If you send an email to Sandy, you could schedule a meeting with him, but he's only here today, and so he might give you some
insight. Yeah.
All right. Thanks, everyone. Let's collect these forms and. Many thanks, everyone, for attending this class. I hope you learned something and I hope you enjoyed it. Please use the course evaluation forms, and I would be also happy to get suggestions from you. So if you could send in email with me what to improve next time, what you liked, what you didn't like, that would be great. And thanks again, everyone. I guess you are free now.